Okay, I'm not sure how many people here know me, but I'm like really excited that the course is going well in the spring. Yeah, it's like this is really awesome, and this is one of the things that really got me into machine learning. Actually, when I first learned about this stuff, I was like, okay, the rabbit hole goes very, very, very deep, and I hope to like show you guys a little bit of like why I think it's so cool today. There will be math, however, it's also going to be like written in plain English, so there's something for everyone here. In my opinion, this is like I say it's like the hardest unit of the course, but that's just because I like it so much that I just wanted to put a lot of content in there so you guys can learn a lot of things. It's pretty awesome. If you're able to take a little more time than usual to like, work on this unit this week, you'll like get a lot out of it. So get started. Yeah, so there's a couple things we're gonna go over. First off, like RL is kind of its own domain in a way. Like a lot of like the terminology in it is kind of encapsulated within RL itself. So a lot of new definitions I need to go over. And then we're going to go over two algorithms and one extension to an algorithm. So the two algorithms, one is policy gradient, which is new. I didn't teach that like before. I usually just do deep Q learning. The other one is the one I usually teach, which is super cool, deep Q learning. I'm going into some problems with RL, and then we're going to conclude, and we can talk about some stuff after. Yeah. Okay, awesome. So reinforcement learning is neither supervised nor unsupervised. It's kind of its own thing, which is pretty cool. At least I'm getting this information from the teacher that teaches RL here. If you see some other stuff online, like sure, but I mean, right from the source. It's separate. Like if you see it's like a different bubble, it's definitely like in ML, although it has like overlap with like control theory and stuff like that. But it's usually considered its own thing, which is nice. And you'll kind of see why as I explain, because like the structure of how the networks learn is very different than like supervised or unsupervised, which you guys have seen so far. So generally, RL, and this is high level stuff, is concerned with the actions of autonomous agents in environments. So I'm going to try and keep it like maybe some consistent analogy throughout the whole lecture. So when I say agent, if it makes it easier for you to think of Mario and you think of environment, you can think of like World 1.1 or something like that. But yeah, this is like reinforcement learning. I think it's super fun and easy to like get into because it's like, oh yeah, I could train a model to like play a game for me, and that's like pretty awesome, right? But it extends like a lot beyond that. It's not always actually just like game-like environments. DeepSeek's fine-tuning, which is the thing that made it one of the things that made it very like powerful despite its like size and the amount of compute used for it, was reinforcement learning actually. And one of the algorithms I talked about today is the baseline for the algorithm that was used in DeepSeek, right? So maybe like there's like the policy gradient, there's one more, and then they use like a little variant of that. So it's not far off from like what people in like industry are using, which is pretty cool. You also have AlphaGo. Who's heard of AlphaGo? Yeah, pretty cool. Yeah, do people not super know about AlphaGo? Because I can really quickly, basically, there's a game called Go. I've never played it myself personally, but it's a huge like state space and lots of complexity, more so than chess. And they were able to train a model using reinforcement learning that could beat like one of the top Go players of all time. And it was a big deal for sure when it came out because it was able to find somewhat new strategies that hadn't been really thought of before, even though this game is like very, very, very old. You also have Alpha Tensor, and more recently, there's another thing that DeepMind came out with. It's like Alpha something else, I forget, but it's for algorithm development. But Alpha Tensor was super cool. It used reinforcement learning and was able to find like a more efficient matrix multiplication method, like in like fewer operations than something normally would take. And they found it through reinforcement learning. So this is all just to motivate that like this isn't like some crazy just like theory with no use. Like this actually is like super cool. But there are some problems that I'll go into later. But this is like really awesome stuff. So if you can think of a problem and write it as like a game, you can use reinforcement learning for it, and you'll probably get better intuition on like why that is as I keep explaining. So defining the game that we're going to play. So this is pretty critical, and I'm going to just like reference these words throughout the rest of the presentation. So let's start off by talking about state. So I just like, you can consider one singular state, this like atomic state, as S, and then you can think of like the set of all possible states in the game as like the calligraphic S over there. So it's often denoted with a subscript of T, so you'll usually see S subscript T, and that means a state at a certain time in the game. So you can think of T equals 0 as like when you boot up the world, right? And as like the timer ticks down and like Mario's moving through the level, you can think of that as like T equals 10, 20, so on and so forth, right? We're going to be talking about discrete time for a lot of these things. Continuous time RL is like a whole different thing, but like you can think of each time step as like kind of its own block, like a snapshot of the world at that time. So that's what states are. It's like a snapshot of the environment with the agent in it at a certain time. They have this property, they're Markovian, which I'll go over what that means later. But if you've taken like, I think 312, then you know what that is. But the states are Markovian. The transitions between states, so like you have S subscript 1 and S subscript 2, how they go, how this like the environment evolves from the first state to the second state, so on and so forth, is dictated by something generally referred to as like environment dynamics. So you can think of like if the dynamics of the environment are like similar to the real world, if I put a ball here at time t equals 0, they'll end on the floor at like t equals 2, right? And that those transitions were done without my influence if I'm the agent. So there's like certain transitions from state to state that can happen with or without an agent's influence. And I'll get into like more exactly what an agent is later, but you can think of the Mario world case for now. You also have actions. This is what the agent can do in the environment. So for example, Mario can jump, move left, move right, shoot a fireball, whatever. They're also denoted with a subscript with respect to time t. So there will often be a state and an action that are paired together. So that is what, in that certain state, that snapshot of the world, what the agent is going to do at that time. So like at time t equals 0, like Mario is going to go right? And then maybe at time t equals 2, his action is jump, something like that, right? They often impact the next state, but it's not deterministic because you can have environment dynamics that are stochastic and that even though Mario wants to jump up, maybe he doesn't or he hits his head against a block. Those are the environment kind of stopping him from doing his action, right? State action pairs, right? So Mario moving right at state S subscript 0 results in a reward, which is a scalar value. I'll go over on the next slide. But you should know that like state, action, and reward are like very intricately linked. So yeah, there's another way to think about it. State, snapshot of the environment, action is what an agent does, just in short form. The agent is the computer model that can interact with the environment and learn from it. So this loop right here is like a very, very standard image. Like you'll probably see it if you ever take like RL. It's just like how the agent and the environment interact with one another. So you have the agent, its role is to take actions and then tell the environment what action it takes. The environment will do dynamics calculations or whatever, and then it'll spit out the future state, right? And then also a reward because we have a state action pair now, right? There's a state, Mario took an action, and he gets a reward for taking that action, right? And those two, the state, the future state, and the reward are fed back into the agent, and that loop is what lets us play the game, basically, right? Environment, I think I've already kind of gone over this a little bit, but environment is just like the world that the agent is in, right? And the agent, most of the time, can interact with the environment, right? And change it to its will. Reward R is also denoted with a subscript with respect to time t. You can also think of it as a function of a state and an action. So like each state action pair has like some kind of reward. Sometimes it's stored in a table if the state space and action space are not like crazy large, but most of the time it's like calculated. So like distance from the goal, you can calculate that given any state and any action, right? At any time. You can just distance from the goal. If you're really far from the goal, you get like a small reward, and if you're really close to the goal, you get like a big reward, right? And it's generally supposed to be like you can think of like a degenerate case where like reward is just 0 all the way through, but that's not what we're doing here. Reward is always just implicitly supposed to be linked to good action. So like high rewards mean that the agent did something good with respect to some goal that it's trying to accomplish. Yeah. So another thing we have here is policy. So policy and agent are also very closely linked, but the policy is kind of like encapsulated within the agent. So it describes how the agent will behave, it is a function of state, and that outputs a distribution over actions. So we can give Mario a state, and it will say, with probability 0.2, I'll move left, and like with 0.8, I'll move right, and with probability 0, I'll jump, right? And then what the agent can do is, given that policy, right, you can think of policy as like just kind of this rule, it's a rule book basically, right, that the agent's going to follow. And then this is like an example of like this equation would represent the agent, but the policy is represented by pi, right? You can look at it for a second, just like basically pick the action with the highest probability and set that to be a subscript t for some state at t, right? And that notation in the pi thing is just like the probability distribution over a given st. It's like conditional. You have a trajectory, which is something that this is where it gets a little more nuanced. So if you're zoning out, let's like lock back in. What you have is trajectory is a sequence of states and actions that ends in a terminal state. You can also call it an episode or a rollout. So if we were to record snapshots at like t equals 0 all the way to like 20, and say at t equals 20, we terminate Mario, that sequence of like state and action pairs all put together in a list maybe, that would be called a trajectory, right? It's literally the trajectory that Mario followed. Then you have return, which is a function of trajectory, which is basically what we're ultimately going to try and maximize. This is where it all comes together, because return is like kind of the function of reward, states, and actions together, because it's a function of trajectory. Basically what it says is, hey, you followed this path, right? You went left, right, up, down, jumped on something, and then terminated your state. How good was that, right? Maybe Mario in this case moved away from the goal. That's a pretty bad trajectory, right? That's not what we're trying to do. Or maybe Mario got like really close to the goal. That trajectory that he followed is going to have a really high return, okay? Here's an example of one type of return function. It's called infinite horizon discounted return. It allows you to calculate the return for an arbitrarily long tau trajectory. And it does this through this discounting factor here, which is put to the power of t. So basically what that means is states that are very close to t equals 0 are considered important, so at the very beginning. And as you go into the future, like future states are considered less important. So it's kind of like you want rewards now, but you also have to consider them in the future, but with less weight. And the reason we have this discounting factor between 0 and 1 is so that this will generally converge under like reasonable conditions, right? Otherwise, you can have return for some trajectory being infinite. Like say, for example, we give Mario a little reward at each time step, and he just stays still, right? And we never terminate him. That means the return for that trajectory, despite him doing nothing, would be infinite. This makes sure that converges to a reasonable number, so it's computable. Okay, everyone following this so far? Right? Okay, good. This was the easiest part of the lecture, so let's get into a little more interesting stuff. So I mentioned the Markovian property for states. States flow through time, as I've described before. The probability of moving from S2 to S3 is unaffected totally by the fact that S1 is in S2's history, right? So the movement of the environment from one state to the next is totally not dependent on what came before, right? You could have some sequence of events A that led up to S2. You can have some sequence of events B that led up to S2. But the probability of transition between S2 to S3 is going to be consistent regardless of the history. This is called memorylessness, which is really important because like later on we're going to go over like one of the actual algorithms, and if we didn't have memorylessness, it would be totally intractable to solve, right? This is the property that it gives us if we have memorylessness, which is pretty important. This is the equation, but in English, it's just the probability of a sequence of events, which it's a trajectory, is the probability of the first state times the probability the second one is there given the first times third given the second, and then like third given the second, fourth given the third, so on and so forth. And notice like we start off with S1, and then we have like S2 given S1, but then this isn't S3 given S2 comma S1. It only depends on S2, right? And so it's the same thing. This is just based on the state before it, not anything before that. There's no t minus 2 here, right? That's pretty important. Okay, everyone get that so far? Please raise your hands if you have any questions, by the way. Yeah, okay. And make a noise or something as well, in case I'm just in the middle of talking. Okay, cool. We're going to go into like the actual algorithm now. Out of curiosity, who has heard of policy gradient before? Yes? Awesome. Okay, so you have some background. Who is doing the technical track at the moment? Anyone? Okay, cool. This will hopefully make the textbook like way easier to digest because I'm going to go over the intuition for some of the stuff that I've explained in there. So, given that we have a defined RL problem, just like I showed in the previous slides, again, just use the analogy of Mario if you need to. We're going to define a policy and have it be parameterized by theta. That's just a fancy way of saying that theta, which are weights or biases or whatnot, influence how the policy behaves. So you can think of pi, as we've shown before, that policy pi, as being represented by a neural network. This kind of ties back into unit 1, or I think it was unit 3 now, is the deep learning unit. Unit 3 is deep learning? Okay, yeah. So we talked about how, I think we talked about, but I'll tell you now, if not, neural networks are like arbitrary function approximators. They theoretically can, approximate any function with an arbitrary level of precision. And we have pi, which is a function, and we want to like learn it or approximate it. That's why we choose a neural network to represent pi, and the weights and biases of this neural network are theta. Okay, so every time you see pi of theta, this is a neural network, right? Just to ground it in reality a little bit. So if an agent follows this policy, pi subscript theta, it should get high returns on average. We can write this in math form as this. We create some function j. Don't ask me why it's called j. That's just like standard notation. It's a function of theta, right? And the expected return based on trajectories that you get from following policy pi subscript theta, we want to maximize this. Okay? The expected return, and this subscript notation is just basically telling you where this tau comes from. This tau isn't random. It's the taus we get, the trajectories we get if we follow a policy, right? Like if we have a policy that always goes to the left, our trajectories will always be trajectories that take us to the left. If our policy always goes to the right, vice versa. So the trajectories are dependent on the policy that we have at the moment. All checking out so far? Okay. So this is interesting. We talked about gradient descent before, but actually policy gradient uses something called gradient ascent because we're trying to maximize this. We want to maximize the expected return, right? If you put a negative sign in front of this, you can use gradient descent, but I think it's cool that they've kind of inverted it here. So what we're going to do is the theta parameters, the weights of the neural network at some kind of iteration, epoch, whatever you want to call it. The next one is just the first one plus the gradient of this function, right? So we want to get this, we have this because we see the neural network. Our job is to like calculate this, okay? So if we can find what this is, given it's equal to this, right? Take the gradient with respect to theta, we can figure out how to like how to actually calculate these numerical values to adjust our weights, right? So there's a proof that's in the textbook, and this is the answer to the proof. So this is policy gradient right here. This equation is policy gradient. It looks like a lot, but it really isn't actually. So I'll step through it bit by bit, and why it's important and cool, because the RL, especially policy gradient, is one of those things, you see the math sometimes, like, if you take machine learning, sometimes it's just symbols, right? It just looks like just Greek and Latin. But the English translation of this actually tells you something pretty cool about like reinforcement learning and like how we can actually go about calculating like the best way to behave, right? So I'm going to color code it. We're going to step through it like bit by bit. Oh, there we go. So why do we care about this? And how you say that is nabla subscript theta of j of theta. Why do we care about that, and why are we trying to calculate this and figure out why it is the way it is because if we can calculate this numerically, right, and we update our parameters, theta, of our neural network using this gradient, that means the next time we use the agent in the environment, we should get a higher return. Mario is going to get closer to the flagpole after this update, right? And that's why it's important. Any questions so far? Yes?
Can you give an example of like what the weights would represent?
Yeah, okay, so it's just going to be, so we'll start off with like the weights are of a neural network, and we'll train those through backpropagation. But one example is, say we start off initializing the neural network, and Mario's policy, which is represented by the neural network, is just moved to the right. He's going to hit a Goomba and die, right? That's not that good. So that trajectory will have very low return. We'll perform this update, and the next time Mario's policy has different parameters, and maybe this time the probability of jump is higher, right? So next time he won't die. That'll give him a higher return. And then it's like a cascading effect. It gets better and better. Okay. Check it out for everyone? Good? Okay, cool. Please raise your hand if you have any questions. So this is the term that maybe looks the scariest, but here's what it is. It's the gradient of the logarithm of the probability that our policy picked action A subscript t given state st, right? What that tells us is that how to adjust the parameters of theta to make the same choice more likely in the future, right? So if this number is very, 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 very high, that means that when we apply this gradient update to the network, taking action AT in state ST is going to be way more likely, right? Maybe things start out 50-50 all the way, but then say this for action move right, because it's a good action to do. So this is action move right, and this is state beginning state. If this computes to be very high, or we scale it up to be very high, and then adjust our policy using what we calculated here, then moving right is going to be a lot more likely. Does that make sense so far? Right. Just the gradient, the logarithm is in there because it's critical for the proof, but it can kind of be a little throw off, but you don't need to worry about the logarithm. Mainly just think about it's the gradient, the policy, action, given a state. If this is high and we apply the gradient update, we're going to be more likely to take those same actions in the future. Does it make sense? Yeah. It's okay. So the intuition from MLE, the reason we applied the logarithm in maximum likelihood estimation was to convert that like product, right, into a summation. In the proof, that happens. So not for it's. I understand the link you're thinking about maximization and gradient ascent. That's not the link, but the link is we wanted to convert the big pi, the product, into a sum. That's why it's there. And this in the proof, this starts off as like a product, and it turns into a sum because we apply the logarithm. That's why it's there. So similar intuition to MLE, but it's more like a math trick. Anything else? Yeah. Okay. All good? Anything? Okay. Awesome. So remember the reminder, like what that actually means. Like if it's high, same actions are more likely. If it's low, the same actions are less likely. And then we have this term here, which is multiplied by the gradient that we calculate. And this is more just direct definition of the return. The return is going to be very high if our trajectory was good, and very low if our trajectory is bad. So knowing this, you can kind of see like how they work together. If the trajectory is really good, we want this value to be really high, so we scale it up like that, right? Because then after we apply that gradient update, we're going to be a lot more likely to take those same actions in the future because it got us a high return, right? And say Mario falls into a lava pit and dies. That's a very, very low return trajectory. So we're going to make this negative, right? And the gradients here are going to be inverted, making that action less likely in the future. Does that check out so far for everyone? Yeah. Okay, awesome. Yeah. And this is not the most critical term, but it makes the math correct. It just means that the tau in the equation, which is kind of implicit, and it's also like written right there, the tau we're calculating the return on comes from sampling trajectories based on the probability that our agent encounters them. This is a little bit of a nuance point, but basically, like if you have a policy, like again, I'll just use the same example. If you have a policy that always moves you to the right, this sampling is going to just be policies that move you to the right all of the trajectories are going to start off going to the right. But as we adjust our policy, maybe this distribution will slowly shift, right? And then you'll get more varied trajectories and whatnot. Yeah, it's pretty important because it's basically like, say for example, right, we were to perform this calculation without that term there, without knowing where the taus came from. Again, you can think of like a degenerate case where you just pick the best trajectories, and then no matter what, this term is going to be high. By restricting the trajectories to be from the distribution of probability of encountering based on some kind of policy that we have, it makes this just more realistic and work out. If you didn't really fully get that, but you got the other parts, you're 99% there. This is just a small nuance point. I didn't want to like leave that like hanging. So, any comments on this so far, policy gradient? I'd love to take like one question. Anybody? It's like a rock solid. Yeah. Oh, I'm so sorry. Yeah, go ahead. Yeah.
I just kind of like one quick question in terms of like high level. Would you say this is kind of similar to MLE in regards to like you're trying to maximize an objective, which is essentially like the reward, and you're trying to find like the parameters for your policy or whatever.
Yeah.
That will give us the highest reward, and those once you figure out whatever policy will give you the best reward, like that's what you're trying to learn. Right?
Yeah, you're trying to learn that. Again, this is going to be like a non-convex optimization problem, so you'll never be able to like jump straight to the best answer. But we're doing gradient ascent, which is kind of similar to gradient descent. It just slowly gets better and better and better and better and better. Our theta is going to slowly be more and more correct. Like say there is like a theta star, like the best possible parameters that will make Mario do amazing, right? Our goal is to get as close to that as possible, right? And theta star would maximize this function, right? So we're getting close to that as possible. That's how the theta plays in. Any other questions? Okay, cool. That's policy gradient. The reason it's important is, the actual proof is in the notebook. You don't have to read this, by the way. I know it's in there. It's a lot. You don't have to read this. If you want to look at the slides, that's totally fine. Yeah, and let me see if I can point out the thing. Yeah, so over here, you're asking about like the logarithm. So there was actually like kind of going back to the probability of a trajectory can be thought of as the probability of all the states occurring one after another. And because the states have the Markovian property, we can write it like this, right? Just a product of all the probabilities of the states. Okay, it's a product. If we apply the logarithm, it turns into a summation, and then we can ultimately like reduce that. Okay, so takeaways from policy gradient, just a good exercise in RL theory in general. It's like building intuition for more complex algorithms. One of the most commonly used like policy gradient-ish methods is called proximal policy optimization, or PPO. Super, 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 super like common. Like you'll see if they use RL, they probably use PPO. A variant of it is used to fine-tune DeepSeek, so it's not too far off. And the difference between like this and PPO is not crazy. It really isn't. So if you ever look into it, you'll probably understand it a lot easier. One thing that's critical is that like in this equation, you'll notice that we don't ever explicitly model the dynamics of the environment, which is huge because, well, we don't have to model the dynamics of the environment to learn a good agent. That saves us a lot of computation power. And in the actual, like in the beginning, like you actually do start off with like, here's your environment dynamics. It's like a function. It ultimately gets canceled out in the proof, which is why policy gradient is useful, because it lets you learn an agent without ever having to model the environment, right? So it's called model free. It's very high variance, and there's a lot of ways to solve that issue. That's like what RL research is, but it's not really that far off from being useful, right? The raw vanilla version is going to be really hard to work with, but like a little changes to it can make it like totally feasible. Okay, so great job. That was the first RL algorithm. I think I'm okay for time. So I'll pause real quick. Any more questions before I go into like the second one? It's like a little more. Okay. All good? Everyone? Okay, awesome, awesome. So the second algorithm is something called Q-learning, which, and I think this is useful to think about because it shows you how many different ways you can kind of approach reinforcement learning. It doesn't just have to be, let's maximize return. Instead, we kind of create this surrogate reward. So a Q value, which we're going to define here, tells you your expected return if you take action A at state S and then act according to policy pi after. So it literally just says like, hey, it's a function of state and action. And Marin's like state 3, here's the first action, plug that in, and it tells you the Q value, like Q is the quality, like the quality of that state action pair. If you had a really good state action pair, the quality should be high because each good state action pairing should take you a little bit closer to like a good trajectory, right? And good trajectories have high returns. However, like bad Q values, like low Q values, mean that you didn't make the best decision, right? And if we say we have this function, right? Like we have Q star, like a quality function, a Q function that tells us exactly what our quality of the state is. We would just pick the action with the largest Q value at each step, right? So now the problem becomes, how do we estimate the Q function, right? So that you kind of get like the surrogate reward, like it's like we're not directly optimizing for return. We're trying to estimate a Q function. Is that checking out so far for everyone? Please raise your hand if you have questions. Okay, cool. The Q function itself, again, I don't know how to like not make this look crazy, but this is the definition of the Q function. Q function, again, is represented by a neural network because they're arbitrary function approximators. In this case, just to remove confusion, instead of theta, I've parameterized it with phi. And it's a function of states and actions, and the output's a scalar. And what it is basically, if I can move to the next slide. Yeah, okay. So you start off by defining S of t, right? Like some time t as S passed into your function. And then you set a subscript t to be the a passed into your function. And that just tells you like, okay, that's where we're starting from, right? Because remember, whole point of the Q function is you start off by taking that action in that state and then moving forward just following policy pi, right? And this, as you can see, this should look familiar. That's just infinite horizon discounted reward. So you can replace this section basically with like R of tau, maybe with like a subscript pi of theta, because it's based on the policy pi, right? So this is like just the math way of like representing with a Q function. It's just, yeah, you start at state S and action A, which is what you pass into the Q function, and it should return to you the expected return over the trajectories from that point onward. The one really interesting fact about the Q function is that it's like recursive. I don't really want to go into like it's not crazy algebra, but the result is just the Q function at some S and T is equal to the reward at S and T plus the Q function at the next state, right? So that recursive property is called the Bellman property. It's critical for like any the Q-learning-esque algorithm because, and as you'll see, the update rule ultimately attempts to minimize the difference between this and that. And the reason that's important is because like it's an interesting way of thinking about optimization. Like you define a function that is like ideal. Like if we were to have this function, then we would solve the problem, right? And then you try and discover the properties of that function, one of them being the Bellman property. And then you start off with a neural network that's randomly initialized, and then try and push it in that direction. Make sense? So it's like you start off with this idealized, most of the time impossible, like formula, and then you like try and figure out like, okay, what properties does it have, and can we like try and enforce those properties using a neural network, right? And the recursiveness of the Q function is one of those properties we're going to like leverage. So, any questions on this one? Yes.
So which side are you trying to, or which side the ideal is the T one, right?
Oh, the Q function is that this Q, this is the same as that. Those are the same function, and we're both are ideal, right? Like there these if this Q subscript phi superscript pi is ideal, then these two sides are equal to one another. And I'll go into like why that exactly is. So I'm going to set up this little problem scenario. We have a state S here that's discovered. Our agent is here at the moment. S prime, which is undiscovered, we haven't looked at it, and just a future one, right? We have a reward at each of those like state action pairs, okay? Now, imagine like the perfect Q function, the one that actually does the job we're asking it to do, right? Don't think about the estimator yet. We're thinking about ideals. So using the Q function here, like if we took a snapshot at this state S, right, and just said, hey, can you give us the Q function here, like for some state action pair at state S? If we use it there, it should be directly equal to using the Q function here plus the reward given between those two states. Because the point of the Q function is you're supposed to be like, hey, I'm going to estimate the reward from here on out. Like that's what the quality function is. Like at this snapshot, can you tell us the reward from here on out? Is it going to be good or bad? That's why it's a high quality is good and low quality is bad. If we're doing that properly, then if we apply the function here, move a step and apply it here, the only difference between the two should be the reward, right? Because like you've kind of eaten up that reward by taking that step. There's less left for you in the future. So the difference between the two functions should just be the reward at that state, an action pair. Does that make sense so far? It's just like the recursive property in motion. Yeah, this is like you can just kind of see this here, right? STAT, you evaluate it, directly equal to the next evaluation. So these two are the same, and this and that are the same. The only difference between them is this reward. Is that good so far? Any questions? Okay. Yeah. So this is where it's actually pretty cool. And if we just have our goal be to get the difference between both sides of the equation to 0 and optimize for that, you can actually solve RL problems. Like even though it's totally just self-contained, like we're not even looking at like return explicitly, right? We're just starting off with a random function and trying to like optimize it. It's like self-learning in a way, right? Like all you're doing is trying to minimize the surprise or TD error, which is represented by delta. Is that right? Pretty sure. Yeah, so we want that to be 0 because the ideal function has that at 0. If this Q function was like perfect, right, like Q star, then this would be true and that delta would always evaluate to 0. But it's not perfect, right? We're trying to learn that perfect function. So that's why we're trying to minimize that. So it's just the ultimate, this is just the minimization. It's just like find the parameters phi of the Q function that will minimize this surprise, delta. And there's like a cool paper came out in like 2009 from like Princeton that talks about how TD error, which is the definition of delta here, is very akin to how the brain learns through surprise, basically. You are given stimulus and there's an expected stimulus at each time, and the difference between them lets your brain update and figure out like, hey, what about my predictions was wrong? And it's interesting because in policy gradient, there was really no explicit prediction of like the future. This is a little more neuroscience inspired by the fact that the whole like driving force behind this algorithm is this predictive function Q. And the goal of it is just to predict the future. And we know some properties about Q that we'd like it to have, and we optimize for those properties, and it works. That's pretty cool, right? Any questions on Q learning? All good? Okay. So one more little thing that makes Q learning interesting is that it's off policy. Meanwhile, policy gradient is on policy. Now, what does that mean exactly? It just means that when you use policy gradient and you like explore some trajectories, you tell Mario to go play his game, and then you collect that information and then perform a gradient step. All those old trajectories that you calculated and stuff like that, they become useless. Like it's not actually safe to use them again because they're old. Like you've changed your policy, so now like what's violated is go back like this term, because after a gradient step, we change theta, and this needs to hold. And if we change theta, this distribution changes, so our old like collected information becomes useless, right? But the thing about Q-learning is that it's off policy because the pi here, like this can be basically whatever. It doesn't matter if it's parameterized by theta or something else. That's useful because you can store all these trajectories in something called a replay buffer, and then you just train your function by sampling from them. So it's a lot more sample efficient. Like you don't need to run your environment as many times to get useful information. You can run it 20 times, 30 times, and you have a lot of data, and you just sample that in mini batches and train your network, and then you can run it again, as opposed to every gradient step having to play the game, right? Yeah, and it's pretty important. Like when I took RL, like they built up to Q learning over like the course of like 4 weeks, and the whole like big wow factor of it was the fact that it was off policy. So maybe I didn't emphasize it here, but this is a big deal. Yeah, that should say Q learning, not policy gradient. But the takeaways from Q learning is that it's model free and off policy, which means that, well, those are just both really good properties to have. It's model free, just like policy gradient was, but now we have the additional thing about off policiness, right? It demonstrates that there's a lot of ways to like solve RL, and I think it's just a pretty cool another exercise in like how you can solve problems like this. Like it's just so interesting. Like here's a function. We want it to be like this. We're gonna like make this neural network act like it, and it works. It actually works. Like you can play pretty complex games with Q learning and a lot of compute. Yeah, and the Bellman property is really important. That's what lets us do this, right? If you have a function with the Bellman property, you can optimize it like Q learning, right? And I was just talking about how like TDR is like neuroscience inspired. Yeah, that was the second RL algorithm. This is twice as much information as I was able to get into people's heads last time I taught this. So that's pretty cool. Yeah. Any questions on Q learning? Yes.
I'm sorry. I'm
No.
still like a little bit confused
Yeah.
how minimizing like the quality of the previous or the difference between the previous state action pair and the like next state action pair like maximizes the reward somehow. Like I'm like a little bit confused.
Yeah. No, totally. It's weird for sure. So first, like I started this off by saying like, imagine we had a perfect Q function. All you would have to do is like start it at a state, feed it every action, and look at which one gave you the highest quality, and you just pick that action, rinse and repeat. So that would be your agent, right? Now that is dependent on the fact that we have a perfect Q function. We don't have that, right? But let's look at theoretically what a perfect Q function would be able to do, right? Definitionally, a Q function is supposed to estimate the future return, right? So for a Q function to be working well, it has to be able to estimate the future rewards well, right? And kind of implicitly, this reward is where ground truth information is injected into the network, right? If we're able to, if the difference between those two sides of the equation truly is zero, that means that this Q value was able to actually compute this accurately, right? Because the difference in, you take a step and you evaluate it, the difference between them means it perfectly captured the reward at time like S between these two. And it's like literally if you like were playing a game and you knew if you press this button, it would make you closer to your goal, like no matter what. Like, hey, which action would give me the best reward? And you just knew that. Of course, you just take the action that gives you the highest reward each time, right? The Q function is kind of like that oracle. that knows that, and we're trying to get our estimator, our neural network, to behave like that oracle, right? Again, it's like there's a function that we can never get. It's theoretical, it's impossible, but it has properties we like. If we can train a network to satisfy those properties, it'll also behave well, right? That's the idea.